Hi, and welcome everybody to this fifth Ignite webinar by Akamas. So super excited to share our lesson learned today to how we optimize the hundreds of Kubernetes clusters and the top lesson that we learned. So that's super great. So we had some very pleased to see this huge number of attendees. So well beyond our expectation. So also please, by the way, I'm Stefano Doni, CTO and co-founder of Akamas, and pleased to share the stage today with Mauro Pessina.
Hello, and thanks for having me today. I work in Akamas as a head of customer success.
All right, so it's great because actually Mauro is leading our customer success team, is bringing more than 15 years of performance engineering experience, so it's gonna be a lot of fun. So a few housekeeping notes before starting, actually. So today we are gonna record the webinar, so you are gonna get the registration link after the event. We are gonna hold also the Q&A session at the end. So I guess let's get started.
So let's start with how to optimize your Kubernetes cluster. Today we'll guide you through a set of common questions we face when dealing with the optimization of Kubernetes cluster. We understand why it's really a complex topic, and we provide a set of best practices that you can apply directly on your environments. So let's start by looking at what a typical Kubernetes optimization stack is. So when dealing with the Kubernetes optimization, you have to start dealing with many different layers. You have to deal with the cloud infrastructure, so you have to consider the cloud price of your instance. You have to consider the sizing and the type of the nodes of your clusters, so you have to consider which cloud instancing you are using, if you set any scaling on the node of your cloud cluster, for example. But also you have to consider the sizing of your pods. You have to consider the vertical scaling of your pods, the requests, the limits of your pods, but also you have to consider if you want or if you can apply some sort of horizontal scaling on your pods. On top of that, you have to consider the language runtime. So you have to consider either if you're running Java, for example, if you're running Node.js, you're running Go, Spark, and so on and so forth. And on top of that, you have to consider also the quality of the service that you are providing to your end user. Each one of these layers features a different set of skills and a different set of parameters that you can tune to optimize the performance of your clusters. Today, basically, we'll see all the layers. We won't see the cloud pricing, so we won't tackle that topic, but we will see how to handle your clusters, how to handle your pods, and why not how to handle the runtimes which runs inside your Kubernetes clusters. Obviously, what we see on the cluster that we are dealing with is that the majority of them face either cost wastage, reliability risk, or both. So, and usually the reason is misconfiguration. Today we present the top 10 lessons learned on the customer that we are working with. Let's start by dealing with the topic of cluster optimization. So cluster optimization basically is how to size our cluster, which instances to select how many nodes to run with for optimizing the cost efficiency and the reliability of our Kubernetes clusters. The first question that we are commonly being asked is, are cluster autoscalers enough to achieve a good Kubernetes resource efficiency? So should we use Kubernetes autoscalers? What we commonly see is that many people think that using cluster autoscaling, self-healing, and so on should automatically apply the maximum possible efficiency on the clusters. The reality is that this is the real world the ideal world that we would like to expect in our environments. But what we commonly see is that the real world is quite different. We can't find an effective bin packing. We see nodes that are underutilized. We see situations that are way far from the maximum efficiency that they can achieve. Let's see some real life scenarios. this is a set of clusters that we analyzed in our experience. What we see is that we see many different type of clusters. We see clusters where efficiency is really low. So if you compare the total CPU allocatable on the cluster and the CPU request used by the workloads running inside that cluster, we can see efficiency which is around 50% in some clusters. While we see some other cluster where the efficiency is better because either they use some sort of cluster autoscaler or they're really good in sizing the cluster. But the real world is that even if you're good in maximizing the efficiency, the ratio between the CPU allocatable and the CPU request, in most cases, the real efficiency of the cluster is really low. And why is that really so low? What we have seen is that in the cluster that we're working with, we usually see that the CPU used by the clusters on average is 3% of the total allocatable CPUs. And to be frankly speaking, the total allocatable CPU is usually what you pay for. So what we see is that you are wasting 97% of what you are paying for. Obviously, this is a huge wastage in terms of cost. And let's see a real world example that we faced in the real world. So this is a Kubernetes cluster, no auto-scaling. What we can see here is that in blue, you can see the CPU usage of the workloads. In light purple, you can see the CPU request, and in dark purple, you see the total CPU allocatable. Obviously, this kind of situation is really far from the best efficiency that you can achieve because you have both an high cluster over provisioning, so the CPU, the total CPU allocatable, is really distant from the CPU request on your cluster. But at the same time, the CPU request is really over provisioned compared to the real workload that you are running inside your clusters. So this is an example of a really inefficient usage of both of the cluster provisioning and also of the request provisioning. But on top of that, let's see what happens when you are good in provisioning your cluster and what happens when you are good in setting your autoscaler, for example. In this case, we see a cluster where the autoscaler is set up in an efficient way. So you can see that the cluster manages to scale in an efficient way, but at the same time, we are really, really far from the real CPU usage. So in this case, we have a situation where we have been good in using the cluster autoscaler, and the two purple lines are really close one to each other. The point is that all this efficiency, potential efficiency, is wasted due to a misconfiguration of the request. And we see that the requests that are asking to the cluster are really far from the CPU that is used on the same cluster. This is the first thing that I wanted to highlight. So there is a high inefficiency in many of the customers that we are dealing with today. So are cluster autoscalers capable of the solution of this problem, and are they capable of selecting the best cloud instances to run our workloads? Well, it's a tough topic to discuss. Why? Because the most common solution that we find for dealing with the cluster autoscaling is the Kubernetes cluster autoscaler and Carpenter. Well, Carpenter is usually smartest than a Kubernetes cluster autoscaler, because the promise of Carpenter is not only to deal with the creation of new nodes if needed to run your pods, but also the promise of Carpenter is to identify a cheap solution to allocate a new node. So when you install Carpenter, when you activate Carpenter in your Kubernetes cluster, you expect him to automatically, basically, identify the best solution for the node that you are allocating. But the reality also for Carpenter is that in many cases, since Carpenter is so cheap in the type of choices that it does, is that in some cases it may select an instance which has a suboptimal performance according to your workloads. So it selects a type of instance that maybe promises to be cheaper than the instances that you are using as of today. But the problem is that if it selects an instance which is maybe too little or uses a wrong CPU, for example, you may face a situation where your cluster has suboptimal performance. And this kind of suboptimal performance may lead to paradoxically increase of the cost of your clusters. We have a deep experience in selecting the best instances for running a Kubernetes workload. This is a real use case example. This is a set of possible cloud instance for Google, for example. You see many different instances. On the y-axis, you can see the performance of the instance, and on the x-axis, you can see the cost of those instances. We deal with a case where the customer was using an instance which was on Intel Cascade Lake with 32 virtual CPUs and 128 gigabytes of memory, and we managed to achieve a number of 65 transactions per second at the price of $1.10 per hour. So this is the baseline situation that we faced in this specific optimization use case. When we started optimizing the application, what we found out is that by changing a different instance, in this case, we managed to find that using a different architecture, AMD EPYC Milan, with the same amount of CPUs and the same amount of memory, we managed to not only double the transaction per second that we managed to achieve for this specific application, but at the same time, we managed to cut down the price, the cost per hour of that instance. So it's possible to experiment with different instances for the cloud, and not always the instance that you are using as of today is the best solution when dealing with a specific use case. So the lesson here is that you should experiment with them and try to find the best solution for your specific workload. So Stefano, I will hand back the presentation to you, because I think you have many interesting consideration to do on how is it possible to work with the pod sizing when dealing with the Kubernetes optimization.
All right, so thanks a lot, Mauro, for the great introduction. I guess we now have much more knowledge about the importance of properly setting the cluster, the instances, the auto-scaling, but actually at the end of the day, the lion's share of the optimization, that's the kind of the key message, still lies in the application space. So we have seen that the cluster auto-scaling can do great things, but if we don't properly realize the pod and right-size the pods, actually we don't really get these expected benefits. And honestly, also, all of your questions from as regard the attendees are all around how do we properly set pod request and limits. So that's something that we have quite a bit of experience. So let's start exactly with this topic. So how do request and limits actually work in Kubernetes? So let's start with some kind of initial 101. So a little bit of refresher. So requests are basically an important concept in Kubernetes. So basically developers, as you know, define the amount of resources of a pod in terms of requests. So requests really is the amount of resources that are guaranteed to the pod. And the important thing to realize is that Kubernetes uses the request in order to schedule the pod. So what that does mean is that actually Kubernetes will look for nodes that has the given amount of CPU and memory requested by the pod available, and then it will actually schedule the pod into the node. So what is very important is that there is no overcommitment. So actually, if the cluster has no requested CPU and memory available, basically there is no more room for additional pod, or this additional pod will require a cluster. We trigger basically the cluster autoscaler, which basically will provision new nodes. And that mechanism basically is only based on the request, which is basically allocated, and it doesn't look Kubernetes doesn't look at all at the actual resource usage. So that's one of the biggest problems that relates to the cost, of course, of properly sizing the pods. The other important aspect is that are related to the limits. So actually, when a pod requests a given amount of CPU and memory, of course, that basically impact the scheduling, but actually the pod has the ability to go above in terms of above the requested value. So what actually is preventing a misbehaving pod from basically saturating the full nodes is limits, of course. So limits actually constrain the amount of resources that a pod can use, and basically different. Kubernetes treats differently CPU limits and memory limits. So the idea is that when CPU is considered a compressible resource, so when the pods kind of reaches the CPU limits, it gets throttled. So this means that basically it will the access to the CPU will be slowed down. So you will perceive you will basically start to experience application performance issues. While on the memory side of things, so it's not about slowing down, it's more about being killed by Kubernetes. So that's what happens. So actually, when the memory usage goes up to the limit, basically Kubernetes will kill the container, and that can create, of course, stability issues. So that's kind of the basics. So one of the things that working with many customers on Kubernetes, we get to work a lot of optimizing requests and limits. So one of the things is that usually comes up is, okay, my teams are already doing setting requests and limits. Typically, they do things manually. They look at dashboards. So I'm all set, right? So I don't need kind of any additional optimization. But the reality is quite different. So that's the result of basically customer that we are working with. If we consider basically the sizing of the pod in terms of CPU usage with respect to the request and limits, in this case with respect to the request, basically we see that the majority of the deployments, 80%, actually have a peak of CPU usage with respect to the request up to 10% or less. So basically that is the way to say that they are highly over provisioned. And that's kind of the typical reaction also from developer team. They tend to kind of oversize the pods in order to not have any kind of issue in production. That's as regard kind of static pods. So when you select basically when you run deployments with a static number of pods, but kind of the same issues applies when using HPA. So most of the time teams say, okay, I use HPA, I'm all efficient because actually HPA is following the traffic, is creating pods, destroying pods, and I'm all set, I'm already done. But if you look at how actually the auto-scaling runs, what we might discover, like in this case, is that the auto-scaling is kind of replicating the inefficiency. So in this case, as you can see, we are looking at a pod subject to auto-scaling. So what you can see is the purple line is the total amount of requested CPU. So as you can see, they go up and down as a result of the auto-scaling. But the reality is that if you look at the CPU usage, again, it's very, very low. So at the end of the day, the HPA is creating more pods, but those pods are kind of empty. So they are not very utilized. And that, again, creates the problem on the fact that the cluster auto-scaling needs on itself to create more nodes, and the cloud bill goes up. So that's kind of basically one of the root of the problems. The other side of things, so most of the time, basically request limits are over provisioned, especially requests, but actually in order to reduce costs, so the idea is that let's kind of shrink the sizing of those pods. But in order to creating this kind of, in order to save costs, of course, doing this may result in kind of problems on the reliability side of things. So as you can see in this chart shows a different analysis we did from another customer. So you can see again, the peak utilization in terms of memory with respect to the request. Again, number of deployments per level of optimization. And you can see, as you can see, basically there are a number of deployments that basically goes above 100%. Of course, we are speaking about requests, so usage can go above the request. But the problem is that, as you know, if your pods request more memory with respect to the use more memory with respect to the request, that you are going to end up in a reliability risk because you are going to kind of get the node full of in terms of memory usage, and then that can trigger basically pod eviction or even cluster stability problems. So that's another kind of problem to avoid. So setting the right request limits is very important. So that's an example where you can see basically memory usage of one of the Kubernetes nodes. As a result of, in this particular case, so the teams were kind of not properly sizing memory requests, so the memory usage was well above the request for different pods. At the end of the day, that kind of local problem created a much bigger stability problem for the cluster itself, because the nodes are basically saturated in terms of memory. So when this happens, the kubelet will start killing the offending pods, possibly even other pods, not just the more problematic one that caused the problem. Also, another bigger problem may be that the kubelet may start, the kernel, the Linux kernel can start killing basically random pods if that the situation is even more severe. So that's one of the effect also of not properly setting the memory request. Kind of a similar problem we can have on the memory limits. Memory limits, of course, are good on that way because they prevent a misbehaving pod from kind of saturating the node. So they are very useful to preserve the cluster kind of stability. But of course, now the problem if memory limits are not properly set is that you will face out of memory kills on the pod. And in this case, we found, for example, pretty significant number of deployments where the memory usage was kind of close to the memory limit. And we are going to also touch about this problem where we are talking about the application runtime and the JVM, because this is very, very related. One of the other lesson which is very interesting, because very often, if you look at, I don't know, in the open source ecosystem, what are the tools that are recommended really to kind of solve the request and limits problem? So VPA comes up a lot, is even kind of recommended officially by Kubernetes. So people kind of typically try to use VPA, but then discover that VPA is not running well, especially for in production. So what is the problem with VPA? There are a couple of well-known issues. In this case, what is interesting is that we had this pod that was running with kind of some with existing requested limits. Then we activated the VPA, and VPA basically what it did is that it's kind of aligned the request to the usage, but in doing so, it actually also significantly reduced the CPU limits, because due to the way the VPA works. So in doing that, actually, this caused pretty significant throttling, CPU throttling, and that translated into the pretty important performance problem into the application itself. So again, VPA has many benefits in that it can help you try to tune the Kubernetes pod, but if not properly configured, especially when tuning the limits, so CPU and memory limits, it can significantly impact the application performance. There are also other drawbacks when we talk about, for example, Java application that we are going to touch later. So basically, our recommendation is that we see typically also applied in other teams is not to use the VPA in production for tuning requested limits. The other big topic that comes up a lot is how do we tune CPU limits? Are they lifesavers or the root of all evil? So basically, CPU limits is highly debated. So also in the question that you asked basically during the subscription of the registration of this webinar. So there are kind of two school of thoughts in a way. So there are lots of people that kind of think CPU limits are kind of not used or even an anti-pattern, because the idea is that everything can be done just by setting the request, right? So if you set a request, you won't suffer a CPU throttling problem. So why bothering and tuning CPU limits? So you need a lot of effort to do that. The idea is that Kubernetes will do just fine. All the work will run just fine, but just by setting the CPU request. On the other side, we have people with a significant production experience, like people at Twitter, people at GitHub and Facebook. There are kind of also many interesting stories as well as regard each incident that you can basically encounter while just using request. So the thing is that, as we said before, request doesn't protect from a misbehaving pod to kind of consume all the resources. So the idea is that also there are many stories about the fact that this can be problematic. So we are kind of two ways to see this picture. So we talk with a lot of teams that are actually trying to understand what is basically the way to set requested limits. So shall we tune limits? Shall we just go with the request? So we try to basically answer this debate not with another theory, but with some kind of quantitative results. So what we did is, let's just do an experiment. So let's pick just one simple CPU node, Kubernetes node, and let's create basically two benchmarks. So let's use one kind of application, which is an e-commerce application that is being that is running with a constant load using a load testing tool. We use, by the way, Google Online Boutique, which is freely available. And then we use kind of a batch job that consumes all of the CPU that gets launched in order to understand if this job that kind of simulates a misbehaving pod in your production actually will be able to impact the application performance. So we evaluate two scenarios. One using just request, and second scenario we use request and limits. So let's see what is happening here. So the first scenario is that let's just use CPU request. So this is basically in the first chart that you see on the top is basically the response time of this application. On the bottom, you see the CPU usage of the Kubernetes node. So as you can see, there are kind of three phases. The first phase, just the application is running, and then we start running the job, which is basically the first job consume kind of a given amount of CPU. The second job basically consume even more CPUs up to 100% the saturation of the node. What is very important is that if you look at the response time, basically the application, the e-commerce application sees a very significant slowdown, up to 3 times higher. So basically, just using CPU request is not protecting the response time of the application if you have kind of shared application is shared with some other pods that are using the CPU. On the second scenario is what is happening if the job is protected with the CPU and limits. So let's say that we just assign one CPU limit. And in this case, even though the job may try to consume all of the CPU, basically it can do so because you have limits, and that basically translates in a much more stable application performance. As you can see, the P95 increased just slightly, but overall the application respond just fine. So that is important, and I guess many people who works in production system, especially in dealing with performance, may realize that why is that? So why is that CPU requests are not enough? The thing is that, of course, using more CPU, that brings higher utilization on the node. And there are basically queuing theory models, or mathematical models that says that as the CPU usage of the node will get higher, basically the response time of the application will start to degrade significantly in a nonlinear fashion. So the problem is that CPU requests cannot really protect the workload because CPU requests just act when the CPU of the node is completely saturated. But if we run basically latency sensitive application, we don't run with 100% CPU, but we tend to run the cluster at much lower level of CPU usage. So that's why CPU requests in this situation are not good enough. So let's now move to the third area. So application runtime. Application runtime is, by the way, is there something that you want to cover, or okay? I'm covering this. So application runtime are very important. Typically, when we speak with DevOps and SREs, we get a question about application runtimes. So why I'm already tuning request limits? It's already difficult because, as we have seen, it's not kind of a work in the park. But the key thing is that why I need to tune also the JVMs for Java application, why I need to look at my runtime, my Golang runtime, my Node.js runtime. I know that, of course, modern JVMs, modern runtime have heuristics that basically automatically adjust with respect to the sizing of the container. So the common reason is that we don't really need to do anything. So my JVMs, my runtime is already understanding that it is running in the container, everything will be just fine. So that's not entirely true for many reasons. One of the things, one of the most problematic area here we are talking about Java is about the Java heap. So as you know, the Java heap is the area of the memory where actually objects gets allocated. So the question is that if I just run my JVM with default settings and I have my container with 1 gig of RAM, how much RAM will be assigned to the Java heap? So the default heuristic is just to assign 25%. So as you can see in this chart, basically it was made by Microsoft. By the way, with 1 gig container, you will get 236 meg of RAM for the heap. So you have kind of quite a bit of wastage in terms of memory if you don't specifically set the memory heap. And by the way, as the container gets smaller, things, as you can see, gets even more complicated and tricky. The other thing is that the JVM it does not only consume the heap memory, but it also consumes an additional part, which is called the Java, the off-heap memory. So that is important because, as you can see in these charts, sometimes we see those kind of memory usage. We analyze pod with the customer, so we see the memory usage start to rise up to the memory limit, and of course, guess what? The pod gets killed. So the typical reaction of the team is that, of course, that might be a memory leak because CPU memory users start to kind of rise slightly, constantly up to the memory limit. The reality is that typically this is not a memory leak. This is not a code problem that needs to be fixed by software engineers, but the reality is that this is a configuration problem. So this is due to the fact that the heap was not properly sized into the container, and basically the JVM started to use the heap and started to use the hop heap memory, and then that translated to an off heap, to basically to an out of memory error in the application. So that is that's important. That's why it is important to still refine basically the amount of memory that is assigned into the Java heap for your Java application. But that is the same, by the way, for Node.js, for .NET, for Golang is a little bit different, but there are similarity there as well. Another part which is interesting is that especially some application like some container images have, for the JVM, have some auto tuning scripts. That's an example that we have come up on working with JBoss on OpenShift. So again, those kind of scripts tries to kind of get rid of the problem. So get rid of this tuning of the JVM. And again, they try to configure automatically the JVM. But what we have seen is that the settings that those kind of magic defaults are apply may be far from being optimal. So what you see on the right is the result of an optimization initiative where you see basically the blue line is the amount of CPU that was being used by the JVM as a result of those automatically recommended configurations. And in the green line, you can see basically the effects of tuning the JVM properly. So in this case, was basically CPU usage was reduced up to 60%, which is pretty significant amount just by tuning the configuration. So in this way, the configuration may be, for example, to be too much biased towards reducing the memory, but you pay that as an additional cost on the CPU, which at the end of the day brings up the cloud base. So again, that's something that, as we are going to see, our recommendation is always review the JVM settings. Another kind of practice which is very funny is what we call cargo cult JVM tuning, because actually we see a lot of analyzing in the wild, lots of JVMs and Java applications. So we get to see hundreds and hundreds of Java command lines. And what we found there is pretty interesting and funny sometimes. So I would say that the most common one is the jar app.jar. So just launching the jar, your app with default settings. So as we have seen in the previous slide, so that is a best practice. That is not a best practice actually, because either you are wasting memory or wasting CPU cycle, as we have seen before, or you are running the risk actually of having performance problems because actually your heap is too small. Second example is that, for example, you may want to use the max RAM percentage, is a newer option that sets basically the heap size with respect to the memory limit. Again, setting this limit as a percentage is kind of risky because it's kind of a relative setting. So if you increase the memory limit of the container, the heap size will be increased accordingly. So again, it becomes kind of harder to understand how much of heap memory will be really reserved for the JVM. And as we have seen, this can bring basically reliability issues. And then we have other kind of funny example where, for example, people basically put in conflicting options or put in duplicated options, or again, some option copy and paste from blog posts that basically have nothing to do with the application that they are running. So this can cause other problem, other problem on the garbage collector, etc. So that's some other things that kind of we recommend against doing. So what are our recommendations? So basically, those are our the lesson that we learned. Not sure, Mauro, you want to do the cluster piece?
Yeah, sure. Let me open up my cam. So the point about cluster sizing is that, first of all, you have to use a cluster autoscaler most of the cases that it can be beneficial for you, but you have to take care to properly align the capacity of the configuration of the autoscaler to fit the requirement of your workloads. So be sure to use an autoscaler, but that autoscaler must be tuned to properly work with the request of your workloads. On the other hand, I suggest you to periodically assess the cloud provider's offering, because new cloud instances keep popping up, and maybe they can have better price performance for your application. So periodically assess them. Try to experiment with them to identify if one of those instances may behave in a better way, in a most cost-efficient way for your application.
All right. So request and limits. So what are we recommending here in terms of CPU? So basically, the first recommendation is kind of well known in a way, which is to kind of put CPU requests to kind of cover to be higher or equal to the CPU used. So that is important, as we have seen in terms as Kubernetes schedule pods based on CPU request. Of course, you may have spikes of CPU usage above the request that may be kind of tolerated, but it's not something that you need to kind of count on, because this additional capacity may not be there, especially if you consider cluster autoscalers like Carpenter, which is kind of instantiating the smallest possible instance that kind of where your pods can fit. This additional capacity basically may not be there. So it's important that requests are properly tuned with respect to the used. CPU limits, as we have seen, are tricky. So it's not that we basically that's true. So they are tricky to be tuned, but actually not using them may basically cause even more problems. So request equal to limits is something that we recommend for the absolutely most business critical application. That translates also in guaranteed quality of service in Kubernetes. So that provides the biggest protection for your workloads. I would say for the most part, CPU limits higher than request is basically the recommendation. But one thing to consider is that basically you need to keep a healthy ratio among limits and requests. This means that if limits are very, very high with respect to requests, it's basically just like not setting them, actually. And also you may have issues where, for example, your application will restart and will try to use all the limits. So you need to kind of find a right balance. So best practice like 5-to-1, 10-to-1 is something that you might consider, also depending on your startup requirements and startup probes, etc. CPU limits can actually be removed in some specific situation. We recommend in general against just removing them for the problem that we have seen. But if you don't have shared environments, or if your app are very well controlled, running on specific nodes, that might be doable actually. So it's not something that we generally recommend as in the first place. Well, while as regard the memory limits, basically in our experience, we always recommend to put the request equal to the limits for the problem that we have seen before. So if usage is higher than request, you can cause significant problems, cluster stability problems. So it's something that I guess you want to avoid. Memory limits still are tricky to be set, of course, because due to what we have seen before, within the application you have a runtime like the JVM, so you need to properly size just what runs within the container, especially the Java heap, also considering the off-heap memory, in order to avoid out-of-memory keys into the pod. Application runtime, so just like the JVM, or even the same is Node.js. I guess we also published recently a blog post on Node.js, kind of the same logic. So the idea is that don't blindly trust the heuristics the ergonomics, because you may end up having problems if you don't set them. So we at least recommend to always set the heap size, possibly even the type of garbage collector, so that you can tune them based on your specific application in order to reduce the cost, but while still matching the performance requirement that you have. And also the other best practice is that we always recommend to tune your JVM, your runtime, at the same time together with the requests and limits of the pod. Why is that? Because those two layers kind of are very interrelated, so they go hand in hand. So for example, if you increase the memory limit, but you don't adjust the heap size, you're not going to be efficient, or even you're in the opposite situation, you're going to have reliability issues. The same is true with garbage collection and CPU limits. So there are very strict relationships. So we always recommend to tune the two layers at the same time. Right. So I guess we are kind of moving towards the end of the webinar. So glad that you were able to stay with us till the end. So still quite a bit of attendees still connected. So thanks for that. So I guess one question that maybe you may be asking is that, is there a better way? So really the job that we see many DevOps teams or SREs is really how do we get basically the most efficient Kubernetes cluster while still preserving application performance and reliability. So optimization is never a one metric game, but it's always a trade-off. And as you can see, it's kind of tricky. So I guess that may resonate with your experience. So I'm happy also to hear from you in the Q&A session. But really, we find a good approach to solve this kind of problem in the wild. So what is the basically the approach that we have recommended is that of course at Akamas we created an optimization platform exactly to solve those problems. So it's an AI-based optimization platform where the people can use and our customers use actually to kind of get rid of those problems. So being AI-based, basically you can literally ask AI what is the goal, so it can bring down your cost and at the same time always keep in mind application performance and reliability. Akamas can actually help you optimize application in two main scenarios. One is what we call offline, which is actually optimizing the environment, basically your application in staging environments, leveraging load test. And the other scenario is optimizing the application directly live in production. So the first use case offline is completely automated. So you get in a matter of one day, one weekend, you'll get already a best recommendation to actually you can then promote it to production, and that will save a lot of money and still preserve application performance. Or if you prefer, if you don't have load testing in place, you can directly go to live and optimize application directly in production. And it's all powered by an AI engine, which is basically based on reinforcement learning, patent algorithms that basically try to solve for you all those kind of problems without the effort, without the deep skills that are required, as we have seen. But also today, what is very important is that I want to announce something new that we are working on. So basically, we working with many customers with on those topics, optimization topics. What we have seen is that actually customers actually find hard to optimize this huge amount of microservices. Also find it hard to kind of understand what is the optimization potential in terms of cost savings. The other challenge that we see is that typically application teams that need to kind of approve the recommendation basically are very busy and then don't have the skills and the effort to do that. So in order to help in those situations, we are actually launching today a new capability into the Akamas portfolio, which is called Akamas Insights for Kubernetes. So Akamas Insights is a new capability within our tool sets that actually is tailored for developers, SREs, and FinOps engineers that actually want to achieve rapid cost savings and improve the reliability of Kubernetes environment with no effort. So the idea is that with Akamas Insights for Kubernetes, you can basically connect to all your Kubernetes environments and instantly understand what is the cost, what is the optimization potential. You can rapidly identify where are the most, basically, the biggest optimization opportunities that you can achieve with the least effort. So it helps you right away to prioritize what are the optimization opportunities across the full stack. Importantly, Insights for Kubernetes can actually highlight reliability risks that you have today. So most likely the first things that you have to fix in order not to impact your business. And also the recommendations are tailored actually and can be easily applied basically without having to do analysis and skills from the team and consider the application runtime. So that is very important. We give recommendation to right size the JVM and also the container request and limits, as we have seen. So very excited for this announcement. So if you wanna learn more, just go to actionable.io/insights. We have a beta program that is running now. So feel free to join us if you want to learn more, and let's get in touch and see how we can help optimize your Kubernetes environments. So again, that is it. So we still have 15 minutes left. I guess it's time to open a Q&A session. All right. So looking at the question that we got, I guess we got a couple of them already from the registration. So one question was, I guess we should have covered that one as regard how should we tune requested limits. Shall we use CPU limits? Shall we not use? Just go with the request. So that I guess that this is something that we cover. Then we have also another question from Darshan about JVM this time. So XMS and XMX values should be the same. So that's also our recommendation. So especially in container environments, so XMX is basically the maximum heap that the JVM can allocate. XMS is the starting heap on the JVM. So typically the JVM has a much lower starting heap, which is due basically for memory efficiency. So if the JVM doesn't need to go to allocate that up to the XMX, basically don't do that. So you will basically run more efficiently on the memory. But in container, in my opinion, things change because actually the memory limit, the request that you have in your pod is 100% dedicated to basically to your JVM. So there is no more sharing with other workloads. So it makes a lot of sense to kind of put XMS and XMS to the same values. Again, many other questions around misconception on requested limits. So that's I guess we should have covered this. Then
we have a question on cost optimization in cloud, and specifically Kubernetes is also very driven by bad application design. How do you take on that problem as well? Well, I can take it. I mean,
yes, please.
Frankly speaking, obviously, if for example, if you have written a wrong query, which is not effective because it uses the resources in not a wise way, or it's using the wrong execution plans, there is little that we can do from a configuration perspective. But what we can do is that we can mitigate the impact of bad code by acting on the configuration. So what we can find is that, for example, if you have some sort of issues at level of, I don't know, you have a memory leak in your application, what we can do is to work on a configuration to mitigate the impact of those memory leak on the application. Obviously, the objective, the final objective would be to remove that kind of issue. But from our standpoint, what we can do is that we can mitigate the impact of that bad application design.
Yes, makes a lot of sense. So we have a couple of best practices from Ted, from T-Mobile, which is great. So basically, Ted is saying CPU limit equals to 3 times the peak demand and round it up to the next whole number. So 1,500 millicores times 3 4,500 millicalls rounded to the limit equal to 5. Okay, that makes sense. So basically, the idea is that you will use a factor. So that's another kind of best practice that we see a lot. So based on your usage, you try to kind of set the limit based on a best practice, a factor, like we've seen, like we have said before. 1 times 5 is one factor. Also, you see CPU requests 80% of the actual usage for 80% of the time. So I guess that's something that you can also do. So in this case, of course, you may have peaks above the request. It's also, I guess, that might be related also to the way that you manage the cluster, because of course, if the peaks are very high, you may not have the capacity on the cluster to do that. But again, I guess it's something to that you can use. All right, then we see always wanted one question related to the XMX at the same size, so similar to what we said before. And one question about AIOps trend. There was about AIOps trend in your product. So that's a great question. So I guess, of course, today AI is kind of revolutionizing entire industries, right? So with Akamas, we are very convinced that AI can benefit SREs and performance engineers, and that's exactly why we introduced AI and machine learning, not today, but more than 5 years ago, actually into the product. So we are actually helping the industry, because AI, of course, and machine learning is much better suited than the human brain to analyze all those time series, considering also that new microservices come and go, the application is scaling, constantly scaling. Also, the traffic by the users is going up and down. So that's something that is very, very hard to do manually. So we really think that using AI is mandatory. It's not only a good idea, but it is mandatory to kind of solve this problem. Of course, the next step is to, like what we do, is automate also the AI recommendation, and that is something that we still see in the industry kind of not fully adopted. So not all teams are ready to kind of automate, but again, the future is coming. Also, Kubernetes is kind of becoming even more dynamic. So you will be able in the future to right size your pods without restarting it. For example, there's a very nice feature that is coming that will enable you to do that. So you will be able to have a smart autoscaler like Akamas that actually takes into consideration all those parameters and basically just apply those to production without you ever noticing, if you want to do this full automation. Also, there is another great question about David from related to the garbage collectors. So that's a great question that we still see. That's one of the great questions that we see a lot of people asking also in our website. What is the best garbage collectors for containerized workloads? For example, ZGC. That's a great question, and honestly, up to now, I have yet to see ZGC doing good in containerized environment. One of the things is that ZGC, just like other garbage collectors like Shenandoah, have been designed to tackle kind of a different challenge, like how do we manage very, very big heaps, like terabytes of heap without having poses. But if we think about the microservice world, most of the time we see JVMs that have, I don't know, 1 gig of memory, 2 gig, 4 gig. I'm not saying that that's the most efficient setup, but still we are more geared towards smaller environment, and that is kind of more suited for to being addressed by collector, even like the serial collector. Serial collector is sometimes not considered as a good one because it's just serial, just to use just one simple thread for garbage collectors. But if you don't have the need to use many more CPU cycles for garbage collector, then maybe serial may do just fine, and that, by the way, may help you save lots of CPU cycle because it's not being used for the GC, it's being used for your application. All right, so I guess that is it. We have not sure if that is a question.
We have a question. This question maybe we didn't answer.
All right, so yeah, Shavant is asking.
It's worth a try.
it's asking a couple of Charlotte and other guys are asking about doing a POC before they sign up. Of course, we can just get in touch. Just sign up for the beta of the Kubernetes Insights, if that is something that might help you, or even kind of try out the full Akamas product that you already have on the market since many years. So just keep in touch, and we'll be happy to see what we can do, how we can help you. Just checking the time. So I think we have 4 minutes left. Any other question, Mauro?
I'm looking at this. I think that we answered basically all the questions. Many of the questions have already been answered during the topic of the question that we received before the sign up to the webinar. So I think that we covered all the questions that we received during the webinar.
All right. So, of course, just let's continue with the conversation. Let's just get in touch on LinkedIn, which is kind of the preferred channel that we use today. So if you have an additional question, you want to kind of go deeper, or perhaps you have different opinions on some of the
if you want to discuss our
that we have shared, of course, we are always happy to basically understand other opinions and learn from you as well. So I guess that should be it.
Thank you for your time.
Thanks a lot for attending. So many people still went through the whole webinar. So thanks a lot. It was great. Thanks for your time, and let's stay in touch until see you in the next episode. Bye bye.
Thank you. Bye.